Next up, Elements of Distributed Systems by Andrew Tanenbaum and Maarten Steen. This provides a comprehensive introduction to the principles and architecture of distributed systems.
Tanenbaum, another giant in the field. His MIX operating system inspired Linux.
Right. The book covers collections of independent computers that need to appear to users as a single coherent system.
And understanding distributed systems is now absolutely fundamental for building any modern scalable software, but especially for large-scale AI systems which are inherently massively distributed.
How so?
Think about training today's huge language models. It requires coordinating potentially thousands of GPUs across a complex network. Serving those models to millions of users requires globally distributed inference infrastructure.
The scale is mind-boggling.
It is. This book gives you the timeless principles for reasoning about these incredibly complex systems. Concepts like transparency making distributed resources appear local to the user or developer. Communication protocols between nodes. Consistency and replication, absolutely crucial for ensuring model updates or training data are correctly and reliably distributed. And fault tolerance, designing systems to gracefully handle the inevitable partial failures of nodes or networks without the whole thing collapsing.
But again, the common misconception. Cloud platforms make this knowledge unnecessary. The cloud handles all the distributed systems problems for me. Is that truly the case?
That is a dangerously tempting but ultimately false oversimplification. Cloud providers offer incredibly powerful building blocks. Yes, things like managed databases, load balancers, message queues.
But they don't design your system for you.
Exactly. They don't absolve the engineer of the responsibility of architecting a coherent, reliable, and scalable system using those blocks. An AI engineer just deploying models onto multiple cloud virtual machines without understanding distributed systems principles. They'll be completely unable to reason about potential failure modes or data consistency issues or performance bottlenecks that arise from the interactions between the components.
Right.
An AI assistant, lacking this fundamental understanding of the laws of physics for distributed systems, cannot solve these emergent system-level problems. This book gives you those laws.
So how would you apply this when designing, say, a scalable AI inference service?
Okay, you need to serve millions of global users. Guided by Tanenbaum's principles, you'd probably choose a client-server architecture, but with multiple replicas of your AI model running behind a sophisticated load balancer. You'd replicate those services across different geographical regions, maybe using cloud availability zones or regions, for both lower latency to users and better fault tolerance if one region has issues. You'd have to critically consider the consistency requirements for model updates. Do all users need to see the new model absolutely simultaneously? Strong consistency, which is hard. Or is it acceptable if updates propagate gradually? Eventual consistency. That's a key architectural trade-off. You'd explicitly design for fault tolerance. What happens if a server running your model crashes? The load balancer needs to detect that and redirect traffic seamlessly. And you'd design for scalability, probably using auto-scaling groups to automatically add or remove model replicas based on current load.
So even if an AI generates the Terraform script or Kubernetes config.
Right. Even if AI helps with the implementation details, this entire design process, making those architectural choices, understanding the trade-offs, requires human judgment grounded in distributed systems principles.
Expertise in distributed systems is clearly one of the most valuable and sought-after skills in tech today, especially in AI.
Without a doubt.
As AI models and the data they consume just keep growing, the complexity of the underlying infrastructure increases exponentially. If you have these skills, you can architect and build truly planet-scale AI systems. You can solve the hardest, most complex production problems, things like debugging race conditions across nodes or handling network partitions gracefully.
The really thorny issues.
And you can command a significant premium in the job market, leading to roles like staff engineer, distributed systems, or principal engineer, AI infrastructure. While AI can write code for one machine pretty well now, designing, building, and managing these global, resilient, scalable systems of machines for modern AI, that remains a deeply human and highly valuable discipline.
It's about orchestrating complexity,